Hi everyone, welcome back, and we are looking now at restricting domains to construct inverses because we have functions like x squared and x, square root of x, that we think should be inverse functions but are not. So can we kind of correct for this feature a little bit? So we're going to see the answer is yes, and we have to talk about graphs of inverse functions first. So you notice I've already drawn f of x equals x squared out here, and I want to draw its reflection. So the reflection is going to be about this line y equals x. So let's draw that in before we do anything else. And you may have an understanding of what reflection means, but let me give you kind of a good way to think about it. Reflection means equal distance from an object. So when we say reflection through the origin, like we do for x cubed, that means that if you look at 2, 8, and -2, -8, those points on the graph are equal distance from the origin. So when we say reflected about a line y equals x, we're going to drop a perpendicular from a point like this. And its reflection is just going to continue in the same direction for an equal amount of distance. So in this example, the reflection of this point, which I'm going to draw in green here, would be right there, since those 2 points are equal. Now, any points that lie on the line, like here and here, they stay on the line because the distance from the line is 0, so the reflection is also going to have distance of 0. Then notice all these points right here are just going to go around like this. This point gets reflected here. This point, let me draw this in red to keep consistent. So if I drop the perpendicular, we'll actually go through here. And so if I continue in the same direction, my reflection of that point is going to be right there. And then I also need to reflect this one other point. So let me get access to my colors again. Let's see. So the reflection of this will go down to here. It drops there. Then we just continue for that length out there. And that gives me that point there. And notice that the reflection of the graph looks the same. So I'll continue this. And this comes out like this and goes like this. And notice that the green circle here is just this black or this green parabola is just this red parabola turned on it, or this black parabola turned on its side. And so this is, but notice now that I am no longer a function. So let's get rid of all this other extra stuff from the reflection here and just look at our two functions here, and notice that this violates the vertical line test, and this is no longer a function. So this is another graphical way of showing that f inverse and the square root function are different things. So let's undo this and let's bring back all that extra junk I just erased, if the computer will cooperate for a second. So we want the square root function to be the inverse of the square function, but we get a whole bunch of extra junk when we do this reflection. And notice that all the extra junk that we don't want is down here at the bottom. So let me pick a different color. Let's do blue. And so all the extra stuff we don't want is coming from this branch of the sideways parabola. But notice that its reflection comes from this part of the original parabola. So if we just get rid of this part, then when we reflect, we don't get any part of this. And notice that all I need to get an inverse function is this right half of the parabola. And to get this right half of the parabola, that's just f of x restricted to the positive axis here. So what we want to do is we want to look at f of x, and we want to redefine it as x squared, where x is greater than or equal to 0. Now this function is 1-to-1, because if we look at any horizontal line, it will just touch that part of the parabola exactly once. So this function now is 1-to-1, and its inverse is the square root function, because now the square root function and the square function, the modified square function, both have the same domain and range, or their domain and range match up. That's what I mean to say, because the domain of the square root function is greater than or equal to 0, and the range here is greater than or equal to 0. The domain of this function is greater than or equal to 0, and the range down here is greater than or equal to 0. So everything now matches up. And this is an important feature when we're going to talk about inverse trigonomic functions, because we're going to have to do this for every trigonomic function. So it's better to get the idea down now than trying to have to learn it while you're trying to learn inverse trig functions. So what did we really do to get this restriction? Well, let's look back at the graph here. So let's get rid of all the inverse stuff. Let's draw back the parabola in. We have this parabola. And what we want to do is we want to pick a domain that still encompasses the entire range. So we have two choices. We can either take the left branch, because this starts at 0 and it will always go to infinity, so it does not change our range, or we could have picked this branch and it would go off to infinity. So this branch right here actually has an inverse itself. That would be if f of x equals the square x squared for x less than or equal to 0, its inverse is the negative square root function. So notice that each branch here actually produces a square root produces an inverse function, because each branch is 1-to-1. So it just depends which one you want to pick, and we always wanted to pick the positive square root, so we're going to pick this right branch here. So when you do an example, so let me pull in an example. I have a good example right in front of me if I can find it. So here it is. So if we look at the function 4 over x squared plus 2, I'm going to cut the whole drawing part out. So here's the graph of this function here, 4 over x squared plus 2. And so we want to come up with an inverse for this. Now, unlike our previous example, we don't get a full range of values, so we have to pick a branch that we want an inverse for. So what we're going to do is we're going to pick this branch. And basically what's going to happen is when we find an inverse, this square is going to give us a plus or minus. This is going to give us the positive branch, and this should give us the negative branch down here. So we want just the inverse that gives us the positive branch. And that's typical when we're dealing with stuff like square roots, for example. So what is our domain restriction? Well, our original domain is negative infinity to 0, union 0 to infinity, because 0 is undefined for this function. So we're just going to take our restricted domain to be the domain of this part, which is lying over this interval. So our restricted domain is now 0 to infinity. Now, once we have that restriction, now we can figure out what our inverse is. So we have y equals 4 over x squared plus 2. Again. So the first thing you have to do is switch the y and the x. And then we're going to solve for y. So this is easily done. I have two choices here, and I'm going to divide both sides by 4 to make my next step obvious. And then when you have two fractions, sorry, that should be y. When you have two fractions equal to each other, you can take the reciprocal of both sides. And then taking the square root of both sides, we get the square root of 4 over x minus 2 equal plus or minus. It's going to equal to y. And since the square root will always spit out positive values, if we match that up with the positive sign, we'll always still get positive or 0 value. Well, we'll never get 0 in this case. We'll always get positive values, which corresponds to this branch right here. But it's going to be reflected about this line right here. So you get some weird thing that kind of looks like, I'm just going to roughly sketch it. This is not going to be accurate, but it's roughly going to look like something like this, for example. 1, 2, 1, 2. Actually, that's actually not bad, except it should have been a little, let's do it one more time. It should have just went through this point a little nicer. But that's actually approximately what it's going to look like. It's actually not very far off. So that's how you find inverses. So that's the last of this section. So I will see you in class.